Hello, this is Chang. For the past 25 years, I have been working on UniData and UniVerse database engines. Today, I'm going to give a brief introduction to the UniVerse recoverable file system. UniData recoverable file system has been running for more than 25 years. Over the years, we have improved and learned a lot from it. The design principle of UniData recoverable file system is to protecting the data. Because back to the old days, the hardware, the software, the operating system were not stable as of today. This is the architecture diagram for UniData recoverable file system. On the left, we have the UniData shell processes, which are actually the database engine process. On the right, this is the place where our data files are located. For non-recoverable files access, the UDT processes directly read, write to the data files. For recoverable files access, it has to go through the system buffer. Each UDT process has a content process called transaction manager process. The transaction manager processes are directly connected with the system buffer. Upon receiving a file open request from its UDT process, the TM process opens the file and registers the file in the AFT table. To read a record, the proper physical log will be set here. Then the TM checks if the pages concerning the record read are in the system buffer. If not, it will load the pages from the database to the system buffer first, then completes the read operation. To update a record, the before image log of the pages to be changed will be write to the log buffer. After the before image log are generated, the TM process starts to change the pages. And after that, then the after image log will be generated here. The after image log actually contains the new value of the record. Those before and after image log will be eventually flushed to their correspondent log files and for possible database recovery usage. The sync daemons, we could have multiple sync daemons, flush the modified pages to the data file. The checkpoint daemon performs the checkpointing so that we will not have a very long database recovery time. All the daemon processes, the same process, the syncd process, the before and after image logger process, and even the transaction manager processes are monitored by the system monitor process. If your system is configured with archiving, the archive process will transfer the after image log to the archive files. And those archive files will be used for media recovery. If the system crashes, the crash recovery first restore the data file to the previous checkpoint at the image level. Then it roll forward the after image logs from the previous checkpoint to the data file to complete the crash recovery. In the case of the whole system failure, we can restore a backup to the data files, then reapply the archive files to the database to complete the database recovery. On the right side of this bar, all the processes, the IPC facilities are owned by the root. On the left side of this bar, those processes are actually individual user processes. Let's go through all the major components in the system diagram. The first one is a transaction manager process. Each UDT process has a company process called transaction manager process. The transaction manager process help their UDT process to access the system buffer. Our UDT process communicates with its TM process through system message queues. If we look into the details of a full cycle of a request, the UDT process firstly sends a message to its TM. TM reads the message, then completes the request. Then it sends a message back to its UDT process. UDT process reads the message, thus completed the request. This full cycle of request contains 4 system calls. The second major component is the AFT, the active file table. All the files in the system buffer must be registered in the AFT table. The files are searched and organized by their file IDs on Unix, which are the I number, D numbers. On Windows, we have something similar. Our open file is identified by its AFID, which is actually the location of the AFT entries. If we look at the details of the AFT, it is organized by sections. We have some sections is evenly divided into some sections. Each section has a concurrent control. And within this section, we have another layer of the hash. So it's 2 layers hashing helps us the performance. The physical log table holds the information about the ownership, the waiting list of system buffer pages. Each of the TM has 1 entry in the physical log table. Inside this entry, all the holding pages and also the pages the TM is waiting for are listed in the entry. The next component is the block group index, the BIG. The BIG is actually the centerpiece of a system buffer. Is used for retrieving, searching pages. A page is identified by its AFID and the offset of the page. The system has multiple of the big entries. On our system, we can have 10,000 or even more. You can configure the such to help your performance. Each of the big entry has its own concurrent control. And within this big entry, we have another layer of hashing. So overall, the first layer distributes our operations to different big. So within that big, we have another. So it's 2 layers of hashing to help the performance of the system buffer. The log buffer for before image and after image log is located here. If we go into the detail structure, it is implemented like such. It's a FIFO buffer. So the engine process, and when writing a log record, it just directly organizes the blocks to the final format, external format of the log file. And a log record, once it's in the buffer, once it's completed, loaded into the buffer, it got a receipt. So the receipt, in the future, you can check if the log record is flashed to disk or still in memory or is being flashed. You can check the status. So the engine process produces the blocks here, and the log process consume and actually flash the organized blocks to the log files. This structure allows us, we could have a very, very, very large log record, even larger than the whole buffer, but those still can be read through to the log files. The Daemon processes. We have pretty much talked about all the Daemon processes, but here we look at them again. The first one is the SM process, the system monitor process. It is the parent of all other child process of the recoverable file system. Same process like the sync Daemon process and before image log process and after image log process and even the team process. And the checkpoint Daemon process mainly performs the checkpoint algorithm, and the sync Daemon process flashing the dirty page, modified pages to the data files to help the checkpoint algorithm. The before image log process and after image logs are responsible for transferring, so flashing the log buffer content to their log files. And the archiving process offloads or transfer the after image log files to the archive log files. The other process, which is a UV restart process, which will be launched to perform the crash recovery and the media recovery when necessary. Database recovery. We have basically 2 types of database recovery. One is crash recovery, and the other one is media recovery. In the case of your system like lost power, or operating system crashes, or even UniData crashes, then we need to perform a crash recovery. The crash recovery involves 2 phases. The first phase is roll back the changes at the image level to a previous checkpoint. The second phase is roll forward the recorded after image logs since the previous checkpoint. So to complete the crash recovery. And the media recovery, what we need to do is first restore the data files with a clean backup, then reapply the archive log files on top of the clean backup to complete the database recovery. UniData recoverable file system has been running for more than 25 years. And when porting this important feature to UniVerse, what we have been very carefully looking at, we think those are the things we can do. First, we want eliminating the IPC between UDT and TM. The second thing, for security, we want create another database user so that we don't have to use the root. Or there are lots of algorithms we reviewed, and then we think we can improve them a lot. And for the another important aspect is that we look at the recovery code. We think we can reuse the replication code to help us for better quality. Another thing is look at the UniData source code streams. We have two different source code streams. One is for recoverable file, the other one for the non-recoverable file. So it's kind of a headache for us. Sometimes if there is a problem we have to fix here, then we have to port it to the other place. So there are some maintenance problem for us for UniData recoverable file system. So based on all of those, and we want to take the 25 plus year experience of UniData, and also we want to change the whole system diagram so to bring us performance and more security. This is a new UniVerse recoverable file system diagram, system architecture diagram. If you look at the diagram, it's pretty much similar to the UniData one. And from this, on the right of this, there is no much change, exactly the same. The only major change is the database engine process. In UniData, it was located here. Now, for UniVerse, we move to here. And this database engine process actually are direct connected with the system buffer. On the bar, on the right side of this bar, all the ownership of the processes and the IPC facilities are owned by the UVDB user, which is a new UniVerse database user. You have to set it up. And on the left side of this bar is the user space, and those processes are still owned by the individual users. And those two processes, it still has a one-on-one relationship, but we will talk about them. They're quite different in the UniData model. Let's look at the two processes here. The front process, we call it in UniVerse, we call this one front process, and this one backend process. And we know, and we now, those are the database engine process, the backend process. So the backend process is launched by its front user process, but the backend process is owned by the UVDB user. And we know that the backend process actually are the database daemon process. Database backend process are the database engine process. They are directly hooked with the system buffer. And the new diagram that the backend process are closely monitored by the cleanup daemon. One important thing is that the background process, since it's owned by UVDB user, but the access right permission for the backend process are checked according to their front process, so that the backend process appears or operates in the access right permissions by their front process. And another very important thing is that all the daemon processes in this picture are owned by UVDB, and the IPC facilities are owned by UVDB as well. Let's talk about the benefits of UniVerse recoverable file system. From what we have done, First, all this hash file, the B tree files, are going through the system buffer. In UniData, we have to choose some of the file to be recoverable and others are not recoverable. But for UniVerse, all the 11.3 data files can be directly accessed in UniVerse recoverable file system. The second thing is that because of the database engine process are directly connected with the system buffer, so we have much better performance. The third thing is that because of the first one, all the files are going through the system buffer, so we are generating before image log, after image logs to protecting the data files. And so we have crash recovery, we have media recovery to those security means to protect your data. So your data is pretty much secured. The next one, on this slide, is that we have a new UVDB user for the Daemon Processes, and also the IPC facilities are owned by UVDB user, and the IPC facilities, the permissions are set to 600, so nobody else can read or write to the IPC facilities. The AFT gave us much better control about the file, and now we know which file is opened by the system and how many processes are opening this file. And in the history, we couldn't tell. And a lot of things, AFT is very well implemented. So in combination with the UV cleanup daemon, we can very precisely maintain this table and in very secure way. And so also we embedded this T30 table into the AFT table. So we dropped the T30 table, and the T30 table manages the UniVerse dynamic file operations. And in the history, it gave us so much trouble. And if it's wrong, and the dynamic file can easily get into corrupted. And also we improved the algorithm, the checkpoint algorithm, the sync daemon algorithm, and the swapping page swapping algorithm, and those algorithms helps us much better in a way of much better performance. Another thing we had done is that the UV cleanup daemon, in the history, it can only detect like data user process in 8 seconds or something. Now we can detect abnormal termination of a UniVerse process in like 0.2 of a second. That is very quick, and this helps us because the process, if holding the system buffer resources, that could drag the other process. So now, because the quick detection, so we can quickly free up the data user process, the resources they are holding, so they're making the system running much smooth. UniVerse recoverable file system feature is released with UniVerse 12.1.1 release. This release contains so many other improvements, such as one thing is I have to talk about is the logical log component. We have replaced the logic log components with UniData one, and UniData one is with much better performance and high scalability. And also we have done so many improvements in the replication and EDA areas. And another thing notable for the is that database startup and shutdown time And in the history, I remember it was taking like 30 seconds or more to start the UniVerse. Now we can start the database in seconds, even with crash recovery. Thank you so much for watching this presentation, and I hope you can give me your valuable feedback. And you can contact me at my email anytime. Thank you. Thank you again.